Hello viewers, welcome to the AC series AC parallel circuits. We are talking about RLC parallel circuit. So one of an example can be as shown in the diagram. So it is shown as resistance in parallel with inductance in parallel with capacitance. Now one thing to be noted over here is when we talk about parallel circuits, it is voltage which is a common quantity, right? So voltage across resistance is equal to voltage across inductance is equal to voltage across capacitance, right? And over here if you apply KCL at this node, it will be whatever is the supply current will be equal to the sum of all these branch currents. So another way to say it is I is equal to vector I is equal to vector IR plus vector IL plus vector IC. Okay, so where IR is current flowing through resistor, IL is current flowing through inductor, and IC is current flowing through capacitor. Okay, so this is that KCL I talked about, that I is equal to IR plus IL plus IC. Okay, V as I as V upon ZT, so total voltage upon total impedance, where IR can be written as V by Z1. Actually it is V upon R, right, because Z1 is equal to R. In the second case it is IL, so IL is equal to V upon Z2, where Z2 is equal to, you can see over here, it is XL2, right? And IC, it will be V upon Z3, where Z3 is equal to XC, isn't it? Okay, so here since voltage is common, I can cancel that V, and I get 1 upon ZT is equal to 1 upon Z1 plus 1 upon Z2 plus 1 upon Z3. Okay, where the ZT is equivalent impedance of the circuit. Okay, similarly you can have one more example where this voltage source is across a parallel combination of Z1 and Z2. Okay, so two impedances are connected in parallel, Z1 and Z2. If I need to find out I1, it will be Z2 upon Z1 plus Z2 into total current I, and if it is current flowing through Z2, it will be Z1 upon Z1 plus Z2 into I. Okay, the formulae are almost same as what we do in case of parallel resistances, right? So it is the opposite resistance which comes into picture in the numerator. Denominator is sum of the two impedances multiplied by current. That means to put it in another way, I'll say the total current, the part of the current that will be flowing through an impedance will be depending on the opposite impedance. Okay, so when I want to find out current flowing through Z1, it is Z2 upon Z1 plus Z2 into I, and when I want to find out the current through Z2, it will be Z1 upon Z1 plus Z2 into I. That means what share of the total current will be flowing through a particular impedance will be depending on the opposite impedance. Okay, yes. Let us proceed. We were talking about the last equation we talked about was 1 upon ZT is equal to 1 upon Z1 plus 1 upon Z2 plus 1 upon Z3. Okay, now let me just introduce to you one more concept over here, that is what is called as admittance. Now what is basically admittance? Admittance is defined as reciprocal of impedance. Okay, so when I say it is like 1 upon Z1, it will be Y1, 1 upon Z2 it will be Y2, 1 upon Z3 it will be Y3. Okay, and 1 upon Z total I can write it as Vy. Okay, so Vy is equal to Vy1 plus Vy2 plus Vy3, or I can write it as Y is equal to Y1 plus Y2 plus Y3. Okay, now whatever is applied to impedance, exactly reverse way is applied to the admittance. Okay, so over here when we say impedances in parallel are Z1 Z2 upon Z1 plus Z2, admittances in parallel are Y1 plus Y2. Okay, so it is that way. Yes. Now let us proceed further. So the total admittance of the circuit will be the phasor sum of admittances of parallel branches. Okay, you can see over here whatever circuit I have drawn in the first diagram, this diagram, naming this as Z1, naming this as Z2, and naming this as Z3. This circuit can be written in terms of Y as shown by this. Okay, so this is how it is redrawn in terms of Y1, Y2 and Y3. Okay, now when I say that the admittance is reciprocal of impedance, let us find out what are the terms involved in it. Okay, so I write Z is equal to R plus Jx, and I have to write Y as 1 upon R plus minus Jx, right? So I multiply numerator and denominator by r minus plus jx. So what do I get? I'll be getting it as r upon z square, because see in the denominator I'll be getting r plus minus jx multiplied by r minus plus jx. Okay, now when you do a plus b into a minus b, it gives you a square minus b square, right? Over here we'll be getting it as r square minus j square x square. Okay, j square is minus 1, so minus of minus becomes plus, so it becomes, the denominator becomes r square plus x square. Am I clear? Okay, I'll repeat it again. See over here, z is equal to r plus minus jx, so y will be equal to reciprocal of it, that means 1 upon r plus minus jx. Okay, I can multiply denominator and numerator by r minus plus jx. Okay, so what do I get? I get r minus plus jx, and in the denominator it is r plus minus jx multiplied by r minus plus jx. Okay, you know that a plus b into a minus b is a square minus b square. Similarly over here we'll be getting r square minus j square x square. Okay, now j square is minus 1, so minus of minus it becomes r square plus x square. Okay, so what do I get? I get r upon z square minus plus j x upon z square. Okay, where r upon z square is written as g, minus plus as it is, j as it is, x upon z square is written as b. Okay, where g is called as conductance and its unit is Siemens. Okay, b is called as susceptance and its unit is Siemens. Okay, so as we have z is equal to r plus minus jx, we have reciprocal of it as y, that is equal to g minus plus jb. Okay, now whatever applies to impedance, exactly the reverse way applies to the admittance. Now what do I mean by this sentence is, basically whenever it is inductive reactance dominant, I get it as r plus jx, right? So over here when it is g plus jb, it says that it is capacitive dominant. Okay, similarly when I write r minus jx, it indicates that it is capacitive dominant circuit, but when I write g minus jb, it indicates that it is inductive dominant circuit. Okay, that is it. So that's the big difference. The sign convention for reactance and susceptance is exactly opposite. Okay, yes. You can see from here whatever I said right now, it can be reflected in this particular admittance triangles. Okay, if you remember, we dealt with impedance triangles in case of RL series circuits, in case of RC series circuits, in case of RLC series circuits, right? Here in the parallel circuits we deal with admittance triangle. Okay, so here in admittance triangle, what is, see, in case of impedance triangle you dealt with r plus minus jx, right? Over here since it is admittance triangle, we'll be dealing with g minus plus jb. Okay, so you can see over here this is g and this is plus jb. Okay, so since it is g plus jb, this is capacitive dominant, so you can say over here this is bc actually. Okay, b suffix c. Why? Because it is capacitive dominant. Okay, similarly you can see in this diagram over here this is g and this is minus jb. Okay, so minus jb indicates that it is inductive dominant circuit, so here you can actually say it as bl. Okay, so if I just take out that impedance triangle out, I'll see it like this. Okay, so g, okay, minus it is jbl, that gives you this as y. Okay, similarly it is g plus jbc, that gives you y, isn't it? So this is actually the inductive dominant circuit, and this is actually capacitive dominant circuit. Okay, that's it. Okay, now when I talk about parallel circuits, the two impedances can thus be converted into two admittances, but the only difference is if the two impedances are connected in parallel, the admittances will be connected. The similar conversion of it will be admittances connected in series, right? And vice versa. Okay, so net current is the phasor sum of branch currents through different elements which are connected in parallel. Okay, so there in case of series circuits we always talked about the current as reference phasor, but over here since voltage is the common quantity, here we'll be taking always voltage as reference phasor. Okay, so you can see over here the different cases drawn in the phasor diagrams. So this is voltage, okay, as reference phasor. We'll be having IR in the same phase, right, because that is the speciality of resistive circuits, that current and voltage are in the same phase, or the phase difference between voltage and current is 0. Okay, so you can see over here IC is drawn like this. Why IC is drawn like this? Because in the this is IC and this is V. You can see over here IL is drawn down, okay, because in the inductive circuit current is lagging, okay, and in the capacitive circuit current is leading. Okay, so always, as I said, the phases are measured in anti-clockwise sense. Okay, so in the anti-clockwise sense, the inductive current has to lag behind and the capacitive current has to lead ahead. Okay, similarly over here this is the case when actually IL is greater than IC. Okay, here it is the case when IC is greater than IL, and here is the case when IC is equal to IL. So let us deal with one case at a time. Let us deal with the first case where inductive current is greater than the capacitive current. Okay, so you can see over here IC is shown leading ahead in the anticlockwise sense from voltage. IR is shown in the same phase as the voltage, because that is the speciality of resistance, and IL is shown exactly 90 degrees lagging behind, because that is the speciality of inductive circuit, that the current is lagging behind. Okay, now as you can see over here, IC is shorter than IL, that means IL is greater than IC. Okay, so what you do is over here we draw a vector IL minus IC, because IL is greater. Okay, and the phasor sum of IR plus IL minus IC is going to give me the net current. Okay, so this is actually the you can see over here, this is the current triangle. Okay, and in this current triangle you can write it as in terms of VY. So this will be VR Y Y1 you can say, and like this, and you will be getting admittance triangle as shown over here. Okay, so let us move ahead for the second one, that is IL is less than IC. Okay, so the difference over here is you can see over here is when VL was greater than VC, your phasor diagram was lying in the first quadrant, but now we are talking about admittance triangles. So these admittance triangles, we are now talking about current triangles and admittance triangle, and not voltage triangle and impedance triangle, right? So when we talk about voltage triangle and impedance triangle, it was when inductive dominant circuits were there, it was all the things in first quadrant. But the same thing when we talk about admittance triangle and current triangle having inductive dominant circuits, the phasor diagram is lying in the fourth quadrant. Okay, similarly you can see in the second case when IL is less than IC, that means it is a capacitive dominant circuit. In this case, if you remember about series circuits, you had impedance triangle and voltage triangle in the fourth quadrant, right? Exactly flipping it vertically, you can get the phasor diagram over here when we talk about current triangle or admittance triangle. Okay, yes, and the last case is when IL is equal to IC. Okay, so when IL is equal to IC, this is what is called as parallel resonance. If you remember in the series resonance, we had VL is equal to VC, and that was for current maximization. Over here IL is equal to IC, and this is for voltage maximization. Okay, so this condition is maximization of voltage. Okay, same as in case of series resonance, you had that resonant frequency as 1 upon 2 pi root LC. Over here also the same frequency, it is 1 upon 2 pi root LC. Okay, as we talked about series resonance, that in case of series resonance reactance is 0. Over here since we are talking about parallel resonance now, the susceptance is 0. Okay, the B factor is actually equal to 0. Yes, the impedance offered by the parallel circuit at resonance is called dynamic impedance, and is given by the same expression as you get in the series resonance. Okay, similarly the quality factor is 1 upon R under root L by C. Okay, that is again the same. Let us deal with few solved problems so that the things are clear in our mind. Let us say we have two impedances 8 plus J6 and 4 plus J4 connected in parallel across 200 volts 50 Hz AC supply. you have to calculate branch currents and total current, and you have to also draw the phasor diagram. Okay, now the very first thing you will be doing is, since these two impedances are connected in parallel, let us first find out what is the net impedance. Z is equal to Z1 Z2 upon Z1 plus Z2. Okay, it is 8 plus J6 into 4 plus J4 upon the sum. Okay, now in the denominator I had to do the addition, so I'll be keeping the same form as rectangular form. But in case of numerator, just because I want to do multiplication, I'll convert this into polar form. I'll be converting this into polar form. Then it will be magnitudes product, and it will be addition of the phases. Okay, so that gives me 56.569 at an angle 81.86. And again I want to do the division now, so I'll be converting this 12 plus J10 into polar form. So that gives me 15.6205 at an angle 39.8056. Okay, now again it's a division, so it will be simply a division of the magnitudes, and it will be numerator's phase minus denominator's phase. Okay, so that gives you 3.6215 at an angle 42.0544 ohms. Okay, this is equivalent impedance, right? Then what do I do is, I can find out I as V by Z. Okay, so V is given as 200 angle 0, Z I have just found out. So this is what is I, 55.2257 at an angle 42.0544. Okay, I1 can be found out as simply V by Z1 instead of calculating like this, or you can calculate it like this also. Okay, because these two are connected in parallel, so the voltage is same. Okay, so current flowing through Z1 will be equal to V by Z1, and current flowing through Z2 will be equal to V by Z2, right? So you can do it that way. The answer will be of course same as whatever I have shown over here, and the answers are like this. Point to remember over here is, the final answer have to be always in the polar form. Okay, yes. Let us proceed further. The second question is, find out the effective admittance between points A and B. Okay, that means you just have to find out admittance, that's all. What do we do is, instead of doing it as Vy is equal to V1 Y1 plus V2 Y2, let us have the same path as we had followed till this class, that we always find out impedance, right? We are more comfortable in impedance rather than admittance, isn't it? Okay, so do it in the impedance way rather than admittance way. Okay, so how do we do? We found out Z as Z1 Z2 upon Z1 plus Z2. Okay, whatever we get is in terms of R plus Jx, right? And Y is equal to G minus plus JB, right? Instead of plus minus, I'll be writing it as minus plus over here. Okay, and it will be R upon Z square plus minus, minus plus it will be J upon X upon Z square. Okay, so what will it be? It will be 22 upon the square Z square. Z you already have, so this is that value, and this is converted into Siemens then. Okay, the next question is, three impedances are connected in parallel across an AC supply. You have to calculate I1 and I3, and I2 is given as 5 amperes. Okay, so Z1 is given to you, Z2 is given to you, and Z3 is given to you. Now since one current is given to you, you can find out the voltage as I2 Z2. Okay, once you find out this voltage, the respective currents can be found out as V by Z1 and V by Z3. Okay, that's all. So parallel circuit problems are actually very easy. Simple mathematical operations are there. You just have to do it very carefully as far as R to P and P to R conversions are concerned. Mind well that whenever it will be addition and subtractions, you will be always having the phasors in the rectangular form, and whenever it will be multiplications and divisions, you will have to have the polar form. Okay, just remember it, and also remember that the final answer has to be in the polar form. Okay, let us stop for here for now. We'll be meeting next in the next lecture for star connected circuits. Okay, thank you.